discuss what is breakdown. There are two type of breakdowns that are observed in diodes. One is Zener diode, and Zener diode is fabricated specially for this breakdown, Zener breakdown. And another one is Avalanche breakdown. We will see the difference between these two breakdowns. Obviously, these two breakdowns are in reverse bias diode only, but depending on the doping of diode, there will be only one breakdown in each diode. Zener diode, Zener breakdown, and Avalanche breakdown. We will see the difference between these two breakdowns. Breakdown is nothing but a sudden increase in current in the diode in reverse bias. If diode is highly doped diode, then only Zener breakdown can be seen. If diode is lightly doped, then the breakdown will be due to avalanche effect. In highly doped diode, which is operated in reverse bias, this is junction, and the depletion layer width, as we have already discussed, that when doping increases, depletion layer width decreases. We have biased this diode in reverse direction, and when this diode is reverse bias, this applied voltage V will almost all the applied voltage will drop across this depletion layer, because this region is conducting, so drop will be very less. This region is conducting, so drop will be very less, and we can neglect these two drops in these two regions, and we will consider that the applied voltage will drop across this depletion layer, and depletion layer with W we can measure, and now the electric field that is acting on the depletion layer can be calculated as V upon W. If W is less, very less, then electric field will be very strong. So in highly doped diode, the electric field at the junction over the depletion layer, across the depletion layer, is very strong, and if depletion the electric field across depletion layer is strong, there may be a possibility of direct rupture of direct direct rupture of covalent bonds, and due to direct rupture of covalent bond, electrons holes are generated, and if charge carriers are generated, current I will increase. So increase in current, sudden increase in current is termed as breakdown of diode. So in this case, breakdown is due to a very strong electric field across the depletion layer in a highly doped PN junction. Now we will see what is avalanche breakdown. In avalanche breakdown, we have a lightly doped diode. If diode is lightly doped, we can see that this time the depletion layer width is very large as compared to earlier case. If depletion layer width is large, then the electric field that induced across the depletion layer will not be sufficiently strong, as in the uh, earlier case it will be weak. So the depletion layer cannot be responsible for breaking of covalent bond. In lightly doped PN junction, for example, this is n-type region and this is p-type region, and this is depletion layer. If some electron if some electron travels into the depletion layer, there may be a possibility that this electron collide with any atom. If it collides with any atom, and if collision is effective, because after collision most of the energy, that is kinetic energy of this electron, will be converted into heat after the collision, and if heat is sufficient, then more number of bonds will be broken, that is charge carriers will be generated, and these charge carriers will start moving under the effect of applied voltage. And if these two electrons collide with another atoms, then more number of electrons will be generated. More number of electrons will be generated. We started with only one electron and now we have four electrons. So in this process we are generating the charge carriers gradually, collision after collision. So this one electron is converted into four electron. This is called avalanche multiplication, and if charge carriers are generated due to avalanche multiplication, the breakdown is called avalanche breakdown. Next difference between two breakdowns is their temperature coefficient and their temperature range. If in a diode we get a breakdown at the applied voltage or the voltage across diode, when breakdown happens, that time if the voltage across diode is less than 6 volt, then we will say this is a Zener breakdown. If at the time of breakdown the voltage across the diode is greater than 6 volt, then we will say this is avalanche breakdown. Next difference is the temperature coefficient. If for example we are getting a breakdown at 3 volts in a diode, and if we increase temperature of diode, then practically it is seen that the breakdown voltage will be either at 2 or 2.5 volts, means the breakdown can be obtained at lower voltages. So I can say that Zener breakdown voltage has negative negative coefficient of temperature. Zener breakdown voltage has negative coefficient of temperature. Similarly, in avalanche breakdown, if we are getting breakdown at 7 volts and if we increase temperature of diode, then practically it is seen that the breakdown will be obtained at higher voltages, either at 8 volt, 9 volt, means the breakdown voltage increases with temperature of the diode. So avalanche breakdown voltage has positive coefficient of temperature. Positive coefficient of temperature. Has positive coefficient of temperature. Now the symbol we will use for Zener diode will be like this. This is anode terminal and this is cathode terminal. This was all about the special purpose diodes. This The Zener diode is used. We'll discuss about applications. It is used as a reference voltage, and it is used in regulator circuits. Regulators we will see in analog electronics detail. Now VI characteristics of this Zener diode will be like this. In forward bias it will operate like normal PN junction, and in reverse bias the voltage across diode, in reverse bias the voltage across diode VR will increase with the supplied voltage up to certain value, that is VBR. When VR equal to VBR, the voltage across diode will remain constant and the current through diode will increase with supplied voltage. So we will get the characteristics like this. This particular region is breakdown region. Breakdown region. And in this particular region it is not conducting, means this is non-conducting region. And in this particular region it is operating like a normal PN junction diode, and an exponential curve will obtain. The cut-in voltage for Zener diode will be 0.7 volt because it is always fabricated with silicon, not to 0.2 volt. Now we will discuss something more about step graded and linearly graded diode. Based on the fabrication process, there are three types. One is step graded diode. A step graded diode is fabricated like this. A single piece material is taken, that is P or N type, and half of this material is doped with other type of impurity. The impurity of other region is kept very large as compared to other. So a step graded diode is either N plus P or P plus N diode. N plus P diode means N region is highly doped. P plus N means P region is highly doped. So we will uh, denote these step graded diodes as N plus P or P plus N diode. If this is a step graded diode, and this diode, if it is P plus N, then the depletion layer width equation we already know, it is twice epsilon upon Q into 1 upon Na plus 1 upon Nb into V naught. This depletion layer is the total depletion layer width. But if we consider the one layer only, then Na will come in this particular part. The depletion layer width equation will contain only Na, not Nd. And if we consider the depletion layer on this N side, then this part only come in the equation. So if P region is highly doped, the depletion layer width will be less as compared to depletion layer width on N side. If this is depletion layer width on P side, and if this is depletion layer width on N side, then we can say that N is very greater than Wn is very greater than Wp, because P region is highly doped. So we can say that in a step graded PN junction, the depletion layer penetrates more into the lightly doped region. And also in a step graded PN junction, the depletion layer width on both the sides and the doping concentration on both the sides are related by the equation which is called charge neutrality equation, which is Wn upon Wp equal to Na upon Nd. This equation can also be written as Wn into Nd equal to Wp into Na. This equation is very important. 2-3 times problems has been asked on this equation. Now linearly graded diode. Linearly graded diode. In linearly graded diode, the doping on both the sides P and N sides are same, but the doping gradually, sorry, in linearly graded diode, the doping in the diode varies linearly as we move from one side to other side, and in step graded PN junction there is sharp change in doping because this region was highly doped and this region was lightly doped. There was sharp change in doping, but in this diode there is linear change in doping, hence called linearly graded diode. In this linearly graded diode, the width of depletion layer will be almost equal on both these sides, W1 and Wp. We can say that for a linearly graded diode, Wp is equal to W1. So this is sufficient for linearly graded diode. In exam, step graded PN junction is asked only. We will solve one problem on step graded PN junction. A step graded PN junction has transition capacitance Ct equal to 2 picofarad when when V0 plus Vr equal to 1 volt. If V0 plus Vr equal to 2 volt, then Ct will be equal to what? We have to calculate transition capacitance Ct. In this question, we can see that the diode is step graded. If the diode is step graded, then for this diode Ct will be inversely proportional to V0 plus Vr raised to power 1 by 2, or Ct is inversely proportional to root of V0 plus Vr. For 1 volt V0 plus Vr 1 volt, the transition capacitance Ct will be equal to 2 picofarad and it is inversely proportional to root of 1 volt. Ct2 for V0 plus Vr equal to 2 volt will be unknown and it is inversely proportional to root of 2 volt. V0 plus Vr is given 2 volt. So Ct1 upon Ct2 is equal to under root 2 upon under root 1. So Ct2 which is to be calculated will be equal to Ct1 upon root 2 and it will be 2 picofarad upon under root 2 will be equal to will be equal to 1.414 picofarad. We'll solve one more problem. Calculate the depletion layer width on n side in an in a step graded PN junction if the doping concentration are Na equal to 10 raised to power 15 per centimeter cube and Nd equal to 5 into 10 raised to power 17 per centimeter cube, and depletion layer width WP is equal to 1 micrometers. Here Na and Nd are given, Wp is given, and it is a step graded PN junction. If it is a step graded PN junction, then Na into Wp will be equal to Nd into Wn. From this equation, we can calculate Wp, which will be Nd upon Na into Wn will be equal to 10 raised to power 5 into 10 raised to power 17 divided by 10 raised to power 15 into 1 micrometers. This will be it will come out to be 500 micrometers.